Thanks everybody for hanging on. I think we'll kick it off now. It's just 2 minutes past 7. So, first of all, good evening, everybody, and you're very welcome to our Leaving Cert Physics webinar, which is set to the backdrop of curriculum reform, the new specification that we're looking at being implemented this year. This is the first installment in our webinar series for Leaving Cert Physics. And tonight, the main focus will be on helping you to get started with the new spec. So what does that mean? Well, we'll look at the new specification itself, how it's changed compared to the outgoing syllabus, how you might get stuck into planning the year ahead, as well as what maybe we can glean from the sample SEC examination papers that were published earlier this year in April. By way of introduction, my name is Conor Walker and I'm the head of post-primary publishing here at Folens, and I'm joined tonight by Dan O'Regan and Robert Nolan. Dan's our long-standing author of Real World Physics, which is a long-standing staple for physics and teachers and students now in schools. And we're going to take a look at the different, different sort of pages and get some insights into the new publication during the course of this publication. Rob is a teacher at Skillwera, Gone Small, and is the co-author of Real World Physics, as well as an author of, in his own right, of the Bridge the Gap Transition Year publication that we've had out for the last couple of years. And Rob's also an examiner, so he brings a wealth of experience along with Dan to this new publication, which we're really excited about. So a bit of housekeeping. The presentation itself will last for about 25 minutes and we'll explore a couple of key areas. So as I mentioned earlier, we look at maybe what's changed with the new spec, particularly what's new, what's out maybe, and how real world physics has changed to address those changes. Then we'll take a look at the planning side of things, where Rob will look at a scheme of work that he's developed and might give you some ideas and insights into how you might approach teaching this year and also in sixth year. Then after that, we'll do a deeper dive into the sample SEC examination papers, where we'll look at some of the common question types that have cropped up in them, as well as some new elements to the papers to possibly keep in mind. There'll be a QA at the end of the session. So if you have any questions during the course of the presentations, just pop it into the chat. There's a button across the top of your screen there, and if you click that and enter your question, we'll get through as many of them as we can at the end of the webinar during the Q&A session. And then just after that, we'll announce the winner of our €100 lifestyle voucher. So make sure to stay with us until then. It could be your lucky day today. So in addition to that, we'll be recording this webinar. So don't worry about taking any screenshots or screen grabs or things like that. The webinar itself will be available to look at again. And we're also going to supply the PowerPoint deck shortly after the webinar. So you'll have access to that very shortly as well. So I think that's enough from me for now. I'll hand you over to Dan first to kick things off. So Dan, over to you and best of luck.
Hi, everybody. You're all very welcome. I look at what's new to the syllabus and what's been removed from it first. Can I have the next slide, please, Rob? Right, new materials. At the start, the nature of scientific knowledge is new to Leaving Cert. Of course, it's been on junior cert for the last, or junior cycle for the last while. Number of new terms there: systematic error, random error, accuracy, precision, percentage error, unit analysis, order of magnitude estimates, and the idea of models in physics. Now, some of these would have been in the old course to small amounts, but there is a very much increased emphasis on them here. And a lot of that material is covered in the first chapter to enable students to come to terms with the new stuff needed. Chapter 2 on reflection of light. There's nothing really new there, except magnification. Formula V over U has been removed, although presumably you could be asked to calculate how much bigger an image is than an object or smaller graphically, but the calculations with the formula are not there. Likewise, images formed by spherical mirrors and the associated numerical problems are not on the specification. If we move to refraction, the formula real depth over apparent depth is no longer on the specification, although the ideas of refraction and things appearing nearer to the surface in liquids or glass, for example, is there, but the numerical calculations based on it should not be. Likewise, the formula n equals 1 over sine c has moved from ordinary level to higher level. Next slide, please, Rob. All right, chapter 4 on lenses. Again, nothing particularly new. Power of a lens has gone. Formula for lenses in contact has gone. And the same thing about magnification of images. That's not on the spec as such. Chapter 5 on displacement, distance and time. Displacement time graphs are specifically mentioned, whereas on the old specs, it was only distance time graphs. So there's a subtle difference that you may need to be careful with your students when the displacement goes negative, that they don't misinterpret that to be something happening with the speed. Chapter 7 on vectors, very much the same, but there are a few changes. You must verify the law of addition of vectors using primary data. In other words, students will have to verify either the parallelogram law or the triangle law in the laboratory themselves. That was not particularly on the previous syllabus, but it was on the one before that. And they've also got to do that in 1 and 2 dimensions. In doing it in 1 dimension is very simple, but it can be tricky to see how it actually verifies the law. One other thing with vectors is it doesn't, ordinary level students, according to the specs, only have to be able to represent and understand what vectors are. But in reality, in the rest of the course, they need to be able to find the resultant of vectors that are collinear, 2 forces acting in opposite directions or the same direction, and that kind of thing. Okay, next slide, Rob, thank you. Chapter on force, mass, and momentum. A new concept, the center of mass, which is, as far as we're concerned, effectively the center of gravity. It's new and it's specifically mentioned. Modeling collisions in 2 dimensions is specifically mentioned at higher level, which is a slight advance on the old syllabus. To verify that A is proportional to 1 over m is new here again. We only had to verify that A was proportional to F, but now we have the second part, and the 2 combined then become the experiment to verify Newton's second law of motion. Also, there's a strange bit at the end there, which you've got to be careful with. Verify using secondary data that collisions are covered by Newton's laws of motion. No, we all know that they are, because conservation of momentum effectively follows from it, but you will need to see an example showing that you can work out what goes on in a collision without ever mentioning the word momentum. There are examples of that done in the book and exercises too. Chapter 9 on pressure and gravity. Well, first of all, we look at what's gone. Archimedes' principle isn't mentioned. The law of flotation isn't. Hydrometers aren't. Diving, the bends, and Boyle's law are not mentioned on the syllabus, so they're all effectively gone. Except, again, the law of flotation follows fairly simply from what students would be expected to know about buoyancy and upthrust, etc. You could probably squeeze the Archimedes principle in there as well, but to see it straightforward is slightly more difficult. But I would be saying something to students about law of flotation as you pass through it. Likewise, moments, levers, couple of a force, torque, conditions for equilibrium, static and dynamic equilibrium, they're also gone, which is a pity for some of it, because you need to understand the idea of a turning force with the electric motor, which is emphasized extra in later chapters. But anyway, that material that was on the old course is also gone. There's also a new experiment here, basically to verify the model P is H rho G, but we've written different there, to verify this model for gravity by measuring the pressure by seeing how the pressure with depth varies in a liquid. It's an experiment that you can see in the textbook. Also new is the idea of the model of gravitational field strength. Now, ultimately, that gravitational field strength is another way of describing what we used to call acceleration due to gravity, and both are dealt with in the book. The formula are effectively the same, but it is a new concept with a new unit that needs to be addressed properly. There's no particular difficulty there. Also, at higher level, there's a formula for escape velocity from a planet or other celestial body. Again, calculations are straightforward. The only thing to watch out for there is the formula is not in the table, so students will have to remember it. But it's not particularly difficult. Next slide, Rob. Work and energy. Fairly straightforward as always. However, there is an experiment to investigate the principle of conservation of energy. I presume there's thousands of ways of doing that. We have looked at one where we look at a trolley hanging and weights hanging off a pulley and accelerates the trolley. And you can see fairly simply using data logging equipment that the loss in potential energy of the masses falling is equal to the gain in kinetic energy of the whole system. And that verifies it in one particular case. Chapter circular motion. Circular motion is de-emphasized a bit. The formula is V equal R omega and F equals M omega R, F equals M R omega squared. And calculations involving radians and angular velocities are gone. However, the idea of constant angular velocity is needed. New material, verification of Kepler's third law using secondary data. Well, that's just to show that for various orbiting bodies, that t squared is proportional to r cubed given data. You'll see some examples in the SEC sample papers. It's straightforward calculation-wise, but it is new for higher level. Also, pupils need to be able to relate the orbits of satellites to their uses. Chapter 12 on Hooke's law and elasticity. What's new? Well, it's an experiment new. That's a fairly straightforward experiment to investigate the force needed to compress or stretch an object. Again, there are different ways of doing it. Verification of Hooke's law is one of the experiments that students must do. That was not in the old course as a mandatory experiment, if you can use those terms. However, pupils would have done it at junior cert, so it's fairly straightforward. At a higher level, the work done in stretching or compressing a string is new. The formula for the energy stored in a compressed spring or other elastic body that obeys Hooke's law is new. That's E is a half K squared. It's in the tables, there's no issue there. And pupils need to solve problems with that. Also, new to ordinary level, Hooke's law is new to ordinary level, solving problems using stretched and compressed materials with the equation F equals minus Ks is new to ordinary level. Simple harmonic motion as such is gone. T is 2 pi over omega. That formula is no longer mentioned. There is, however, some reference to the pendulum to measure G, which would be included as an experiment, a standalone experiment, but the theory behind it is not on the course. Next one there, Rob, please. Right, chapter 13 on thermometers. It's a fairly short chapter, just basic ideas are required, but they need to be known well. And analyze the suitability for materials for use as thermometers is specifically mentioned. Your chapter on heat is a fairly large chapter, very much like the old material, but there are some changes. New material, determine specific heat capacity of a solid and a liquid using secondary data. You could argue we were doing that already. Determine latent heat of vaporization of steam or fusion of ice using primary data. That means that pupils must be able to do an experiment to measure latent heat, and higher level need to be able to measure specific latent heat. Basically, specific latent heat as such is gone from the ordinary level course. But the experiment is essentially the same with a slight modification, and ordinary level people may very well do a simpler version using a polystyrene cup or something like that, rather than getting into crazy mathematical details. Next piece was on the old course, but it's slight modifications. Investigate the impact of insulation on energy consumption and sustainability using secondary sources. And there's an increased emphasis on calculations with U values and solving problems with U value. Technically, you could have argued that was on the old course, but there is an increased emphasis on it. Next one there, Rob, please. Right, chapter 15 on waves. New would be the relationship between amplitude and energy carried by a wave. Not a large topic, but it's specifically mentioned. What has gone is stationary longitudinal waves is out, so we don't have to worry about those. Go to sound in chapter 16. There's a new experiment where pupils have to relate the pitch and loudness of sounds to their wave characteristics using observation. Okay, that's discussed in the book. It's basically seeing how the pitch and the loudness and the wave characteristics, wavelength and amplitude, frequency and amplitude correspond. Investigate the use of ultrasound in technological and medical contexts. Again, it's specifically mentioned here, but that would have sort of been on the old specs as well. Verify the model F is 1 over 2L, the square root of T over mu. No, first of all, that formula as such wasn't on the ordinary level course before. There were bits of it. I think it was F is inversely proportional to L, but now the full formula is there and pupils have got to do an experiment to verify it. That doesn't mean that pupils don't need to know how to deal with F being proportional to 1 over L or F being proportional to the square root of T, because they are effectively parts of that bigger experiment. What's gone? The concept of overtones and mentioning of that is gone. Intensity of sound, sound intensity level, decibels, gone. Sound level meter, measurement of speed of sound in the experiments we used to in that, that's all gone as well. So this area is reduced a piece. Chapter 17, which is on the wave nature of light. Technical details of the spectrometer are not examinable, they're not mentioned on it. Derivation of n lambda equals d sine theta is gone. The derivation, obviously, pupils need to use it, but ordinary level pupils no longer need to use that formula. Stress polarization, primary and secondary colors, addition of colored lights, all that material is not on the specification. Next one there, Rob, please. Excuse me. Static electricity. New. Conservation of charge and interactions is specifically mentioned. You could argue it's not specifically new because we were dealing with it all along. The electric field is a model for non-contact interaction between charged objects. Well, electric field was there already, but the way they describe it is different. There's no mention of demonstration of electric fields, so pupils wouldn't be examined in that particular experiment. New to ordinary level. The definition of electric field strength is new to ordinary level. But they wouldn't be doing any calculations because, according to the specs, the formula E equals F over Q is not on ordinary level, but they need to be able to give the definition of electric field strength. Coulomb's law formula has moved to higher level, but ordinary level pupils will still need to know that it's an example of an inverse square law, and presumably that the force depends on the product of the charges, but they wouldn't be doing numerical calculations with the full version of the formula. Chapter 19, nothing particularly new there, except anything and everything to do with capacitance is gone. So that's something. 21, no changes there. 22. This will be resistance, basically. The experiment to measure resistivity is no longer on. Of course, pupils could be asked questions on it because any of the things in it, you could just give a pupil the relevant data and they should be able to deal with that to actually calculate the resistivity, but they don't have to do the experiment themselves in class or anything. Anything to do with the Wheatstone bridge and meter bridge, that's gone as well. Next chapter on the heating effect of an electric current. There's no longer any reference to the word Joule's law. The experiment to verify Joule's law is gone. Chemical effect and electrolytes, gone. Conduction in ionic solutions and gases is also gone. Chapter 24 on semiconductors, a lot of it is the same as the old specification in content-wise. However, the transistor and the transistor acting as a switch is new. No, it was previously one of the options, but I believe the vast majority of people didn't do it. So it's might be effectively new to a lot of people. But again, it's straightforward, and it is there was an example of it on the state examination sample papers, but that is new. Next one there, Rob, if you're still here. Hello, hi. Right, chapter 26, the simple DC motor and the role of the split ring commutator. Now, on the old specs, we all basically look at the operation of a motor, the turning effect on a coil, but officially, the description of a DC motor was not in the normal part of the course. It was again in the electricity option at the end. But the simple DC motor now and the role of the split ring commutator is specifically mentioned, and everybody needs to know about it, ordinary level and higher level. The derivation of the formula F equals BQV is gone. The definition of the ampere is gone because they changed it. And the formula F equals BIL for the force on a conductor is moved to higher level. So ordinary level pupils would not be doing calculations with that. However, they still need to know the three factors on which the force depends: the magnetic field, the current, and the length of the conductor. Right, we'll move on. 27, electromagnetic induction. Well, what's new? Well, the use of the term the generator effect, that's only another word for electromagnetic induction. Investigation of transmission losses in the national grid and issues related to electrical generation and distribution using secondary sources. What is new is the AC and the DC generator and their components and how they operate. Again, that was on the optional section on the previous syllabus, but it is now specifically mentioned here for both ordinary level and higher level. So that's one to watch. What's gone? An experiment to compare peak and RMS values, no mention of it. Self-induction is gone. Alternating current and inductors is gone. Alternating current and capacitors, gone. New to ordinary level on paper anyway is mutual inductance. They knew about it anyway from the transformer on the old course, but it is specifically mentioned here that they need to know the word. Also, the formula IP VP equals ISVS is specifically mentioned in the syllabus for both ordinary and higher level. In the old syllabus, it wasn't specifically mentioned, but I think it was accepted that pupils needed to know it. Now, the concept magnetic flux as phi equals BA, that has moved to higher level. So ordinary level pupils will have no need to do calculations with that. However, in the specs in one place, the word flux is used in ordinary level material, but they don't mean it in the mathematical sense. When they said the changing magnetic flux for ordinary level, that would just be a changing magnetic field. Faraday's law and Lenz's law are gone from ordinary level. They've moved to higher level. The chapter on the electron, the photoelectric effect and that stuff, pretty much the same, and for most. Explain how the photoelectric emission supports the particle model of light. Well, again, you probably really were teaching that all along, but it's specifically mentioned here. Applications of cathode ray tube other than the X-ray tube are not mentioned, like the cathode ray tube in a television, but that's all outdated stuff anyway, so they're not, pupils don't have to really worry about them. The atom, chapter 29, radioactivity. There's mention of the Thomson model of the atom, which wasn't on the old spec. It's fairly straightforward. There's increased emphasis on calculations with E2 minus E1 equals HF. And that formula is no longer in the ordinary level course, which it was. It's moved to higher level. And you'll see again, later, I think, or maybe I can't remember. Do we have one here now? But that stuff is examples of it were on the state examinations sample paper again. Again, they were relatively straightforward. Okay, Rob, one more. Chapter 30, which is fission, fusion, and nuclear energy. There's a few new things in there. The idea of mass defect, binding energy, and nuclear stability. And that's also new to ordinary level. And again, you'll see examples of it in the sample papers. You've probably seen them already. At ordinary level, the calculations are fairly straightforward. At higher level, you just got to be careful with all the numbers that are flying around, but it's straightforward. Cockcroft and Walton experiment is new to ordinary level. Previously, that was higher level only. And in your particle physics standard model, there's some changes there. The evolving standard model is new. Fermions and bosons, they're new. Describing matter in terms of the particles and antiparticles using secondary sources, well, that's the same. The important thing here, though, is that most of the basic material in this chapter is now on ordinary level. Before, this chapter was higher level only. Obviously, the ordinary level pupils wouldn't be dealing with it in great depth. Okay, that about finishes that for the moment. So back to you, Rob.
Thanks for that, Dan. Hopefully you can hear me okay now. So I'm going to be going through the scheme of work. I know a lot of you are probably at kind of the planning stage, or you might have even started teaching now at this stage, the new spec. But I'll just go through what we've put together as far as the scheme of work goes. I'll try and explain it, and I'll show you a couple of pictures basically from it, and hopefully they'll be able to share that with you then fairly soon after this if you haven't got your hands on it already. So there we are. So just to explain how I've kind of laid it out, I suppose, and then I'll show you a couple of images from it. I was kind of debating myself how to order it, and I know there's a lot of different ways that teachers teach the course. Like two popular places to start would be to start with maybe optics or mechanics. And rather than trying to kind of fit everything, I just said I'd follow the order that it is in the book. There's many people I know teach it that way anyhow. And if not, it should be easy enough for you to chop and change it and edit it, and that's true for every. I've highlighted the higher level only material in bold. It was similar to what Dan had previously in his what's in, what's out. If there's something specific to higher level, I'm just trying to highlight it as much as possible. And then in it, I have various different columns where I'm trying to link back to the spec as much as possible. So for each of the different topics, different units, I have learning outcomes linking back to the actual learning outcome from the specification. So you can kind of have a read of that as well, just to make sure you're kind of covering what needs to be covered, I suppose, for that particular topic. I tried to link to the unifying strand as well, because I think Connor will be talking about it later. It's the sort of thing that you might cover in chapter 1 to a certain extent at the start, but then you're constantly dipping back into it all the time. You're constantly referring back to it as you work through the topics. And we have lots of places in the book which kind of highlight that, but this is just another kind of highlight that I've tried to do, just pointing out where we've addressed the different outcomes in the learning outcomes in the specification. I've also gone through the sample papers and picked out the questions that are relevant to each topic. I've included them in the assessment column, as well as a few other bits and pieces that you could use as kind of assessment at the end of a topic. So I'll show you an image there. Hopefully you can see it there. It's slightly obscure now on my one, but that's all right. So I've divided into units of work. So there's an early unit of work, 2 of them from the scheme. So refraction of light, part 1 and part 2. There's the topics to be covered. There's the learning outcomes, which instead of writing them out in full, I wrote kind of using codes instead. So hopefully that'll make sense to you. It's in strand 2, and it's the 3.1 is the third kind of section of that, and the first learning outcome then from that block of learning outcomes. I've included reference to the chapter as well, which you may or may not like, but again, you should be able to edit and change this as you like if you're using it for yourself. I've tried to link into the unifying strand. So those topics I have mentioned there in the link to unifying strand, they're using the same subheadings that they use in the spec. And I'm just trying to point out where we're using some of these things within the chapter. And then over on the right, assessment and also the experiments. So I've got experiments down the bottom of the assessment column. In the middle there using, sorry, I'll just move this so I can see it myself. In the middle there, we've got the questions. So S1, for example, there in blue, the first one, that refers to sample paper 1 and the order level sample paper, and it's question 3 from that is on this topic. And then in red there, I have the higher level sample papers. So sample paper 2, question 5, parts of that are to do with this particular part of refraction. And I'm hoping teachers will find that useful. It took a bit to kind of arrange everything and to put it into the right place, but it'll just save you having to do the same thing, you know, where you can just go through those questions. That'll give you a few sample paper questions. Some of these are in the book already, you know, in various different forms, again, as we'll talk about later. But just so you have your own, you know, kind of, so you know how you can assess it, I suppose, elicit them out. And then the experiments, some of them in bold as well for the ones that are higher level only, like the bottom one there, verifying the model, n is equal to 1 over sine c. So that's kind of the general layout of the scheme, and that's one of the examples there. Here's one from a little later on, which you might get to maybe kind of around Christmas time or after Christmas. There's heat transfer and temperature change, just to show you kind of the same thing again. I have the higher level only bit there again, specific latent heat, kind of just to try and highlight that for us as much as possible so we know where the divisions are, and questions, assessment, all that sort of stuff laid out to the right of the scheme there. Here's one then from later on in resistance, and I think I have one more then from much later on. So fission, fusion, nuclear energy, and the two particle physics. So it's the sort of thing you might need to play around with, I suppose, to kind of make it fit for you. And you know, you might want to add things to it. As I said, you might want to remove things. You know, there might be things in here that you don't necessarily do, or you wouldn't like to highlight in your own scheme, and you can change it and, you know, do what you like with it there, really. So hopefully it'll be shared in an editable form so that you can do that. I think that is the plan anyhow. So that's the scheme of work. You know, feel free to ask a few questions at the end, I suppose, on it. But in the meantime, that's just a small look at it rather than reading through the whole thing and reading it out. I said I'd just highlight a couple of things. So that's the scheme of work. The last thing then we were going to talk about was just a couple of things from the exam papers. I know Dan is there as well, and he can definitely feel free to chime in on any of these, but I'll talk about the first couple of things, and then Dan will see us out at the end with one or two bits. So while looking at the papers, we basically tried to kind of pick out things that were maybe a little different to how they would have been asked before. And that's what we're focusing on today, like different styles of questions to how we'd have had them previously. And we're just going to try and highlight those. We'll try and point out where we have answers and things like that for them, because the vast majority of these we have done as either worked examples or SEC examples inside in the book, and just show you some of these different types of questions and, you know, I suppose discuss what we think of them, I suppose. Just some things about the exam paper itself. So I'm sure many of you have looked at it already. You know, it's 7 questions, do 6. They have to complete question 1, and then they have a choice of the remainder of the paper, which is much less choice than we would have had previously. Means for anyone kind of making out schemes and thinking of maybe leaving topics out or anything like that, I don't think it'll really be viable in the new spec. Just because we don't know exactly what will go into these questions, and it could be a mix of different topics. And in fact, most of them are a mix of many different topics. If you look at any of the full questions, question 1 in particular tends to have 4 or 5 different topics spread throughout it with a variety of different types of questions. These are some of then the new types of questions we saw, the ones that were maybe a little bit different to what we'd seen previously. So questions that involve kind of completing diagrams. You know, obviously that's kind of a side effect of having the question and the answer all together in the one booklet. There's nothing too challenging about them, but really just to point them out as something a bit different to what we're used to. Tick the box questions, which I know I would have scoffed a little bit at when I saw them, but they're actually harder than they look. Some of them in particular, ones where you're asked to maybe justify or explain afterwards, can take a bit more thinking than you might think by looking at it first. And sometimes being given multiple choices can actually kind of put you off in a way. So a little harder than I thought at first glance, those style of ones. Predicting and justifying is everywhere as well. There's lots of different places where a student is asked to say what will happen and then to explain why it is happening. And they can be very challenging from what we think. There's a lot of deep thinking required to really kind of explain it accurately. So, you know, we'll show you a few examples of them when we'll talk about what we think. And then for graphs, you know, there's quite a change in the graphs compared to what was there before. Before it was mostly an emphasis on kind of the drawing of graphs. That's still there, and they still do have you know, questions on drawing a graph, but there's more of an emphasis now on kind of interpreting the graph. Or trying to do other things with graphs that we're maybe not as used to before. So that one will be probably one of the bigger changes in terms of just how we handle graphs, really. Experiments 2, a lot less emphasis on the experiments that the students will be carrying out from what we've seen from these sample papers. So it is still there, it is still present, but it's just not with the same, we don't have that section A that we had before where it was just the mandatory experiments, so it is what it is. And then there's one or two types of questions where you're maybe given a formula. This is again quite new to us too. There's one in particular example that I'm sure many of you saw that I've picked out. Not really challenging questions, but just very new to us. And then at the end, Dan will take over for this one. We have some of the new topics. So there are things that weren't there before, and we'll just be pointing out again where we have these as answers in the book, and trying to show you that we have model answers, model solutions to all these new topics questions. So just start having a look at them, just some of the completing diagrams ones. So here's the first one, which you may have seen. I think it's from sample paper 1. An object is placed 30 centimeters in front of a convex lens of focal length 10 centimeters. By choosing a suitable scale, draw a ray diagram to determine an approximate image. So what makes this one very, very different is it's drawing a ray diagram to scale, where they'll have to choose their own appropriate scale, and then I presume based on the boxes, and then draw the ray diagram using that scale and get an actual answer for the image distance from that. Very different to what we'd have had before. Not exceptionally challenging. It might take a bit of practice, that's all. For your students and for maybe for ourselves as well. But it is something new, something different there, and it's something we haven't seen not for a long while. So yeah, drawing a ray diagram to scale. Here's another one where you're being asked to kind of complete a diagram. So this one, a metal plate with threshold frequency F0 has electromagnetic radiation of frequency F incident on it. The frequency F and the intensity I of the radiation landing on the plate can be varied. I might not read out all the questions if that's all right, but that's the question we have there. And you're asked to complete that diagram then as your answer. And for this one, I just said I'd include, this is a cutting from the textbook. So if you go to this particular topic, same for any of these questions, if you go to the topic, go to the chapter and have a look, you should find either a SEC examination question box, or it might be down as a worked example and changed ever so slightly. And you'll find the question and a solution to go along with it. So there's our solution for the diagram for this one. Again, not too much being asked for it. A bit of thinking may be required for this one, which makes it a bit more challenging again than it looks at first glance. And that's kind of my thoughts in general for the papers. They're more difficult than they look, I think. Certainly the higher level ones are. But there it is again, something a bit different there. Here's one again that kind of has a diagram and some boxes where they're being asked to kind of rate where the magnetic field for this one will be strongest in these different positions there, P, O, N, and M. Which is again a bit different, not something that we'd have seen much of before. And again, I think that's part of just the new way they're laying out the paper that kind of allows for these styles of questions and things like that. Again, solutions to all these will be in the book too. Tick the box questions. As I said, some of them can be a bit more challenging than you might think. So here's this one. The central magnet is rotated by the bicycle wheel. Identify when the magnetic flux through the coils is at its greatest. So the answer is the last one that you'd have to tick, and you'd have to try and justify it and talk about the strength of the magnetic field, and things like that. Tough one to get an actual full answer to structure it nicely and to put it together nicely. But again, we have those sorts of things in the book. So it should be a handy reference for us. And I'm sure we'll see more variety of questions like this too. So it'll keep us on our toes. But again, I wouldn't dismiss it. Again, my first thoughts looking at these were that this looks a little simple, but there's a bit more to it when you actually sit down to try and answer it. I included part 2 of this one just to again show you another example of a solution, and it was kind of the best place I could find to include it. Trickier than it looks again, this one. I won't call through the whole solution, but as was mentioned earlier, you should be able to access all these slides, and if you have access to the book, obviously digitally maybe at the moment, you should be able to look through and to find the solution there again if you go to the relevant chapter, go to the relevant topic. So just included kind of for a reference in that. Here's another tick the box one that again might be more challenging maybe for your students. I know a lot of you would find it straightforward enough, but still more difficult than I thought at first glance. So this one, the magnitude of the charge Q2 is doubled and the distance between the charges is tripled. So it's the first one of these options would be what you'd want. In the box, I presume it's for workings out. It's not clear whether they have to show this or justify this or anything like that. But, it is what it is. Again, maybe a little more challenging than it looks at first, I think, these tick the box ones. And for this one, this is both a sketch and tick the box. So again, they show up often enough, these styles of questions. where they have to sketch the magnetic field around the solenoid onto the paper, and then have to pick, as the current exits the solenoid, its magnitude is the same. They have to pick which of those options they want to pick for it. So again, not to be dismissed. That's kind of why I include that, because maybe it was just me, but I had that opinion looking at it. But definitely they're more challenging than they look. And looking at that, you might kind of second guess yourself, looking at all these different possible answers. In a way, it might be better to answer a question like this by covering the answers, reading it and trying to think what would the answer be yourself, and then looking at the answers afterwards to see, does the answer you thought actually fit with the answers that were given? Because sometimes you can confuse yourself looking at all the options that are given. Then there's the predicting and justifying ones. So here's one that I selected again, I think from the first sample paper. The mass of a rocket can be over 7 by 10 to the power of 5 kgs. Predict how the mass of a rocket affects its escape velocity. And again, justify your answers. So not the hardest predicting and justifying question there, but still, might take a bit of thinking. The prediction is the mass increases it. If you go back to that formula, Dan, I haven't quite learned it yet in my head, but Dan had it on one of the previous slides. You'll find mass in that formula, you'll find escape velocity, and you'll see that they're proportional to each other. So something like that should kind of be the focus of your answer when trying to justify it, which I think, again, students might find a bit difficult, and we might have to, again, practice doing this more often, making a prediction and then trying to justify it and say why it happens. Often it does seem to be maths that forms the justification, but not always. Here's an example of one where it's not always. So this one, there are 3 different diagrams, 3 different circuits. All of the bulbs and batteries are identical, and it's asking you to circle the bulbs that have the least amount of current flowing through them. And again, justify your answer. In a way, this one would be easier if they'd given us numbers. You'd be able to just slot the numbers in and work out your currents, and away you go. Well, in the absence of numbers, you have to talk about kind of current splitting and all of these things. You'd be circling those two, the 2 over on the right hand side there, and trying to talk something along those lines again, saying that the current divides along both paths, and so is less than in the main path of the circuit there. So again, a little challenging, I think, and does require you to really think about what you know. Like, I think it actually probes a little bit deeper into understanding than we'd have had even on the previous syllabus. There was a lot more emphasis on definitions and things like that, whereas they really do seem to be kind of testing your understanding of things with these new questions, which makes it challenging. So we'll see how it goes once we see more of them. For graphs then, I'll just point out a couple of things. So the first thing is to point out some of the new things about graphs. So you might have seen there, I had this one up. This is obviously something very new. The addition of error bars itself is kind of a new thing. But then on top of that, we've got the model. So these two combined make this question a very, very different question to what we've seen before. I don't think it's actually a particularly challenging question aside from that. Once you kind of get over the idea of the model and get over the error bars, what I'd ask you to do is reasonably straightforward, but it is very different. It's something that we haven't seen much before. You're being given this formula. We don't really know where this came from. Some student came up with it from their data or from their model or whatever. And you're being asked then to use that formula for various things. I think I included the parts of this question here. Oh yeah. So use the student's mathematical model to determine as accurately as possible the difference between the value their model predicts for the current at a potential difference of 2.5 volts and the actual value the student obtained. So all you need to do for that one is just plug numbers into the formula. So plug in 2.5 for V and come up with an answer for I, and then compare that to the answer that the student gets from their data points. So that's all. So the data point there is at 0.037 or so. If you fill your numbers into the model, it'll be close enough to that, and you have to basically show those 2 numbers. And then there's a bit of discussion, again, a bit of commenting and things like that come up later. Oh, sorry, it asks you to use the data point and error bar plotted by the student to estimate the range of current values the student would accept when the voltage V is 2.5 volts. So the error bars there, if you look at them, you're basically just looking at what range those error bars fall into. They're covering 4 of the little boxes. So I think that's 0.004 just from reading it. So not the most difficult. It can be very intimidating when you first see it. And when I first saw that question, I was kind of groaning, but it's not that bad when you get into it and start to kind of work with error bars data. It's obviously very new to us, something we might have to include a little bit in some of our experiments, maybe not every single experiment, but it might be a good thing to include for some, just to again, kind of emphasize that these error bars are a thing that we might see in certain questions. So that's kind of the new style of graph questions. I included this as well just to show you that it's not all new. So there's a good old-fashioned drawing of a graph, displacement and time. So that's reassuring at least to see that that's there. I could only find one at higher level, but that means there may be more. So we don't know that we may see more of these as kind of time goes on. The kind of good old-fashioned drawing of a graph, where we still need to teach them those skills to put together a graph coherently. It's not the easiest graph to draw either. So they really they need to know their graphing, basically. There is something unusual, though, happens with the kind of second half of that question. So immediately after that, they take you've drawn your graph. Your graph for this one, by the way, is a curved line. It's not a straight line. And you can see it from the numbers that it's increasing, greater and greater as time goes on. And then what it does is it takes a small little kind of piece of that. So they're looking between t is equal to 3.9 seconds and t is equal to 4.1 seconds. And they've taken that small little section of it and drawn that in a graph. And you can see that the graph is forming a straight line, which is not what your graph looks like up above. And they're asking you to explain why the graph looks like this, basically. Why does this graph appear to represent a different type of motion to the data in the table? For that, you'd be having to talk about kind of the sensitivity of your equipment, the fact that the velocity change, over such a small time frame is very small. So your equipment mightn't be sensitive enough to actually pick up that very small velocity change, that very small, slope to the graph. Which again, very, very different. Not the sort of thing we'd have had to consider before, and the sort of thing you might, at first glance, kind of panic about and think, geez, what do I have to say here? But something along those lines, I think, would get across the point that it's how sensitive the equipment is really for it. And here's where you're given a new formula. Again, this is one that I picked out that I think could be very intimidating when you first see it. Certainly as a teacher, I thought it was an intimidating looking question when I saw it. I was thinking, geez, do we have to have this in the book or have to have this covered? But it just seems to be a sort of one where there is a link to the spec. They're talking about the Doppler effect and blood flow. And then a new formula is given. So this formula here, delta F is equal to 2F V cos theta over C. And they're asking you to do a calculation with that. So again, very, very, I think, intimidating for us to look at, or I find it is anyhow. But I think students would have no problem with this. They're kind of used to seeing new formula all the time anyhow, as they're learning new chapters and new topics. So to them, this is just another formula. They're told what all the letters mean, and they're given the information within the paragraph of text above, or within the question itself, to answer this question. So realistically, it's not that much being asked of them. It's just very new to us, seeing these new formulas. So again, might be something to bear in mind if you come across a formula somewhere or something. Might be good to throw a new formula at them every once in a while, just to make sure they're used to just seeing something completely blind and just having to put numbers into it. I don't know would they be asked to do much more than that with a new formula like this, to be honest, because it's quite limited how much further they could push it. But this is, again, a very different type of question to, I think, what we'd have seen before. And that's that. And if Dan is there, we have the new topics. Are you there, Dan?
Yeah.
Yeah. I might mute myself now and let you chat away there. Oh, I think you've muted yourself, Dan.
Can you hear me now?
Yeah, I can hear you now.
And camera as well, I suppose. Yeah. Right. Oh. Yeah. Right. Here's one of the new things we mentioned in the introductory chapter. Unit analysis. Pupils have now got to do that, verify that by checking the units of each quantity on both sides of this formula, whether they're the same or different. In this case, it turns out they're both the same. And you're asked, using a unit analysis, evaluate the validity of the student's conclusion. Well, you got to be careful with that. Excuse me. If the units on both sides are the same, it means that the formula could be valid. It doesn't necessarily mean it is, it means the formula is a valid formula, but it doesn't mean it's the correct one for the situation being described. There are many examples of this throughout the text, and the pupils eventually will find it very easy. Okay, Rob, next one. Right, again, there's a number of new things here in this one. The diameter of a wire is being measured. A student reads the value of that when using a calipers with that size graduations. And then they do it with a micrometer screw gauge. Calculate the reduction in percentage error. The first new thing here, which wasn't specifically mentioned on the old syllabus, and that is not specifically mentioned here either, but it's estimating the error when you're using some instrument. Typically, we would take the estimated error there to be 1/10 of the smallest graduation, and you would then run through the calculation using that, getting the percentage error for each. And again, percentage error wasn't specifically mentioned on the old syllabus, but most pupils will have met it in their maths course anyway. Then you calculate both percentage errors and subtract. In the final piece, is the student certain to have improved the reading's accuracy, precision, or both? Again, that could require a bit of thought. I think pupils will tend to go for more accuracy, but that's not necessarily so, because there's no discussion as to whether the micrometer screw gauge has systematic error in it. So the most thing we could say is that precision remains the same, but accuracy not necessarily. Okay, Rob, next one. Okay, this is a straightforward question with numbers, just verifying that Kepler's third law holds. In other words, you've got to calculate t squared over r cubed for each of the moons and find out that the ratio is the same. Okay, Rob, next. Right, this is a question on the photoelectric effect. It's, how would I put it? It's different to the type of question you would have seen before in Leaving Cert exam papers. But if you read through it very carefully, you realize, yes, this is the same stuff. And that occurred in some of the questions Robert has as well. You have to know, get your pupils to read their questions very carefully, see what they're given, because there's an awful lot of information given that's not standing out and is needed to answer various questions. And that's in line as well with the new specs, where we're trying to get pupils to work with information that they're given rather than have them memorizing stuff. Now, there is memory required in the course, but the emphasis is less. So a lot of questions have the information needed to do various calculations, etc., in them, in the question. But there's a lot to be read to find that information. Anyway, this is a question on the photoelectric effect. Two parallel plates in an evacuated tube. Blue light shines on the separation is that the variable resistor is adjusted until the potential difference across it is 0.5 volts. Calculate the increase in the kinetic energy of the electrons as they move across the tube. That's standard stuff from the old course. The graph 2819 plots the variation of the kinetic energy of the electrons against the displacement from X. So as you get further from X, which is the photosensitive plate, then the kinetic energy increases, again, as you'd expect. So that graph should make sense to a pupil. But when you're at S equal to 0, that's the energy of the electrons that have just been emitted. And although it doesn't show it on the scale, the last point at the right-hand side of the graph is 70 centimeters. So that corresponds to the kinetic energy of the electrons striking the plate Y. By drawing on the graph, show how the graph can be used to estimate the increase in kinetic energy. Well, obviously you subtract the energy from the graph, from the graph where it strikes the EK axis when S is 0, when S is 70, and subtract the 2. I think that's on the solution below, Rob. It's indicated. Have you the solution here? Yeah. It's the difference between the red energy at the top and the blue one at the bottom. That's the gain in going across. Could we go back again, Rob?
Yeah. I'll go back there now. 2 seconds.
Take your time.
Oh, I've gone forward. Sorry. There we are.
Sorry for interrupting, guys. I'm just conscious of time. We're pushing nearly 8 o'clock, and I don't know if there are elements to this that maybe we could skip through, because we will be sharing the deck. If there's any key points, Dan, that you want to flag. Sorry for, I don't mean to interrupt it. I'm just conscious of time, and people may have to move along.
Okay.
Thanks so much.
That's in the book, and there's a full solution to it. So that's fine. Yeah. On you go, Rob.
Let's move on. So this one's here.
Again, this is a nice question. Start of it looks complicated, but again, all the information that you need is given to you there. Even if you didn't know what a fission reaction was, the reaction is there. You got to fill it out.
And the solutions are there too.
Part G. If you go back one step, Rob.
Part D, was it?
Yeah.
Part D is there. Back to the question. Yeah.
Where am I gone? The energy produced in the fission is that 2 grams of hydrogen contains the same number of nucleus 235 of uranium 235. Okay, we're talking about the mole there, but that's not on the specs. Identify by calculation which fuel produces more energy per gram when they undergo the nuclear reaction shown. Right, if you move on to the solution, it's very straightforward, but it's very tricky. You have to think very carefully. It's not physics, it's just counting and being careful and watching out. Took me a while to get that the first time I looked at it, to get that precisely right and make it legible. But again, the information is there and it's absolutely perfect. Have we another one, or is that it?
There's one more, this stuff.
One more. This was, again, back to the point I made already. You must read your question carefully. You could look at that and say it's gobbledygook. But in fact, everything you need to answer the question, other than one or two small bits at the end, which you know anyway from the previous course or from simpler information, is given here. It's more like, I don't know how you describe it. You look at this, you're given what everything means, and then you're asked to interpret other diagrams containing the same stuff.
Yeah.
So even though it might look very difficult, it is very straightforward if you read it again and again and see what you're given. Okay, I'll stop there, Connor.
That's great, Dan. Rob, thanks so much for that. I'm sorry for cutting you short, but you covered so much ground there in a short space of time. Great to see so much engagement in the chat as well. Lots of gratitude, lots of good questions and interaction between the teachers on the chat itself. So we'll get to some of the questions and answering them as quickly as we can shortly. But this is just to say that this whole presentation coincides with the publication of our new Real World Physics second edition, which we're really excited about. It's, as I said, it's been a book that's been in existence for many, many years, and we're really happy to take the opportunity with the new specification to update it, revamp it, realign it to the exam and to the curriculum, and bring about lots of new resources, both print and digital, to bring about a really solid and excellent teaching package, which Dan and Rob have put so much thought and effort into. So next slide there, Rob, very quickly.
Yep.
So I just thought I'd quickly run through very quickly the elements of the teaching package. So we start with the print. We've got the textbook. So in it you'll find lots of high quality physics that many teachers would be familiar with from the first edition. But beyond that, we've also completely revised the content of the book so that it's aligned with the curriculum. We have more exam style questions in there. And then obviously there's the unifying strand piece, which is threaded throughout the book where appropriate. Then we have, which will be published and available next month, the assessment and exam guide workbook, which will include comprehensive practice for knowledge consolidation and revision. But then critically, we're also going to include a lot of exam style questions. We'll have an exam style questions section in each chapter of that book so that you have more of that type of question and variety of question types for your students so that they're battle hardened, hopefully, by the time they get to sixth year and sitting their leaving certificate examination. And then later on this year, we'll be developing the laboratory investigations book, which is effectively the student's laboratory notebook, where we will feature in that topic overviews, procedural information, space for students, obviously, to record their experiments, and then questions at the end to reflect on the experiments that they've conducted and what they've learned or what they might do differently if they were to conduct those experiments again. Next there. Rob, thanks. I'm kind of regretting adding these slides in now because we're running against the clock, but this is just to give you a whistle-stop tour of the book. The books, it's available online on Folan's Hive if you want to take a look at the online version, and you can obviously get inspection copies now, which have been printed from your work. But this is just very quickly to show you the structure of each chapter. So we have at the beginning the relevant strands listed. We have the teaching objectives, keywords, clear definitions are set out throughout the book in green boxes, and the relevant formula and the page references in the formula and tables booklet are provided. Then we have a full range in every chapter of worked examples and end of section exercises as well. So there's comprehensive practice throughout. Then we have student experiments and demonstration and experiments. So the student experiments are linked to those experiments that are not really mandatory anymore. They're not called mandatory, but they would be the required experiments such that you can achieve the learning outcomes. And it's about the collection of primary data. And then we have shorter demonstration experiments, which would cover more shorter, and they cover more conceptual information around the study of physics and the use of different equipment. As you can see there, there's QR codes attached to each that link us to the experiment videos, which are brand new, and we've got a full range of those for the program. And these are just some stills from that. They're in development and will be available on Folan's Hive very soon, later in the next couple. Well, we're hoping actually we'll be able to upload a couple for the first few chapters later on this week. So the full complement will be available very soon. And as you can see, special call out to our esteemed colleague, Sean Finn there in the middle, who helped us out. And also thanks to Ryan Gallagher and to Stephen Murphy, who allowed us to use of the Eureka Labs to produce those videos. So that's a brand new thing I hope that you'll see value in. We cover within the textbook lots of exam related and exam focused content, and we cover even more of that with the abundance of examination questions that we have, or style questions that we have in the exam and assessment guide. Rob, maybe next again.
Yep.
And just, you'll be familiar with this, but any higher level only content is marked with those margin markers that you can see marked HL. Okay. And then these are how chapters conclude, with a summary of what I should know, and then also then importantly, learning outcome reviews for students so that they can assess what they've learned. This is just a quick show of how we cover the unifying strands. So we have a reference chapter at the beginning, which covers the nature of science, the scientific process, how do we get scientific knowledge, how it changes, hypothesis testing, all of those different things. And then threaded throughout the book, then we also discuss the application of science. Rob, I think there's a few more bits there in relation to energy and sustainability. We reference the relevant scientists who develop those theories. And then models, this just as an example of us discussing the evolution of theories or models in physics, where we moved from a more simplistic ray model to a more complicated, sophisticated model of waves, when we understood that there were limitations to the ray model, and further investigations were done to test that. And then this is just an example from, I think, the nuclear chapter, which covers the environmental impact of fission reactor. So it's threaded throughout every chapter of the book. On the online side, we then offer also a scheme of work, which Rob gave some snapshots of there. So we're making the full scheme available and editable this week on Folan's Hive. We're also going to create a full range of chapter PowerPoints, which you'll be familiar from the current edition, but we'll have new improved versions for that. So the chapters for optics will be available from this week. And we will be uploading more and more digital resources over the course of the next couple of weeks as each chapter resource is completed. We have all the experiment videos that I mentioned, so they're going to be going up online shortly, and they're a brand new, excellent set of resources that both you and your students will have access to. And then the fully worked solutions for both the textbook and the workbook, again, being posted for the first couple of chapters this week, and then thereafter we will kind of provide a rolling update and uploading of resources, so that you're not left wanting for any resources as the weeks progress. Okay, so next up. So if you have any questions, you can just contact your local rep. If you don't know who they are, just go to folans.ie and look for the contact your rep link. Type in your school information, and that'll throw back your rep's contact details. Inspection copies, as I said, are available, and we've also got the book available online if you need to look at it this evening. Your reps are fully knowledgeable. Any news and updates that you need on real world physics as things change, they'll give you, and any support that you need for the book scheme that you'll be implementing for Leaving Cert, they can provide that too. All right, sorry, I've zipped through things. Okay, so this is to the Q&A. I just want to thank everybody in advance and apologize also for any questions that I don't get to. I tried to answer as much as I could during the course of the webinar itself, but there are some things that kind of common threads and themes. So a lot of questions, guys, to do with experiments and equipment specifically. So experiment on the conservation of energy, why data logger? What other methods can be used, or using equipment from the old course? That this person doesn't have a data logger, so is wondering what they may use in its stead for conducting those types of experiments, if there are other options.
Will I take that one?
Sure, Rob, yeah.
Go on. So yeah, there's lots of different ways, in particular with kind of the mechanics experiments of doing them, and we try to kind of reflect a range of different equipment inside the textbook. So you'll see some experiments being done with ticker timers and ticker tape, some being done with light gates and air tracks and things like that, and some using data loggers as well. It's just a case of using whatever you have access to, do you know? So if you have ticker tape machines and you're happy with those, you should be able to carry out the conservation of energy experiment with that. And same for any of the experiments we've done. We've tried to kind of reflect a lot of different things, but again, it's hard to hit. We couldn't have 3 copies of each experiment or more even inside in the book. So we selected one that we think is good, and obviously all of those options there for mechanics are viable for those experiments. So
And just a question just on that, 2 spin-off points maybe. One is to do, it's just popping in, a few people are mentioning this, to do with mandatory experiments. Is the idea of the mandatory experiment in the same way that it was for the old syllabus? Has that slightly changed, or what's your approach? I guess, I mean, I've touched on the fact that there are primary data collection, it's referenced in the learning outcomes. So I suppose they effectively in name become the required mandatory experiments, but maybe there's a bit more flexibility to teachers in what they select to do.
Yeah, like so they don't use the word mandatory anymore. They call them, well, we're calling them student experiments. They only make reference to maybe, like if you look at the spec, it'll say to do something like verify a model using primary data and secondary data or something to that effect. And that's how they reference the experiment. So there is no mandatory experiment list. There's no section A in the paper where you have your 4 or 5 mandatory experiments that are going to come up every single year. So it's quite different from that respect. They are still expected to collect the primary data, and they definitely are well worth doing, but they're not mandatory in the same way they were before.
Yeah. And just in relation then to, there's a couple of questions there, I think, related to time, the time challenges. Like, have Dan and Robert any thoughts on time difference between what's been taken out and what's gone? The specs, not timed, but previous one was time to teach the course. So in terms of the time challenges and figuring things out, I suppose, in terms of you approaching the book and the planning and so forth, what would your thoughts be on that?
Well, there's a lot gone out, but there's still a lot come in, and there's a lot more extra depth required of the student. So there's going to be no great glut of free time or anything.
No.
It's going to be as busy as it ever was, if not busier, especially with the time that will be required for the assessment at the end.
Yeah. I'd agree with Dan there. Like you kind of have to leave some time for this project that we'll be figuring out as well. So it really will put pressure on time wise. Like I find I'm often there until Easter or later trying to finish the old course, and it'll be the exact same with the new course, or maybe even tighter. So timing is going to be a big issue, I'd say. All right.
There were a number of questions just asked about the AAC, which I responded to in the chat, but I just thought I'd mention it here up front as well. We haven't published anything in print with respect to the AAC, I suppose, because there's still a lot to be decided and a lot of information still to be released about that. So we felt it would probably be a little bit foolhardy to put anything in print in any of our books about that until the dust settles. So we are aware of that and the need for support in that space, and possibly what we might do. And we're looking at this as the situation evolves, and it is quite fluid, but certainly we will provide online support and resources to support that. As I mentioned, this is part one in a series of webinars that we'll be doing with respect to the specifications for all the Leaving Cert science subjects, and no doubt the AAC will be a hot topic and something that we will cover and provide some thoughts and suggestions on when that comes through. So definitely it hasn't been ignored, and we've been quite intentional in our approach to not cover it in print just yet. But as and when we have more information on it, we'd like to speak to teachers, obviously, to hear what your thoughts are around it, and then provide resources to you and to your students to help navigate that new aspect of assessment as best as you can. Okay, so I think that's it. We'll put a cap on it. We're pushing well past 10 past 8. So what I might just suggest there is if we can maybe get the winner of our of our lifestyle voucher for €100. I don't know, Sarah, can you post the name? Okay, hang on. It is
I think it was you, Rob.
Orla
Sometimes
Coffee.
happens.
Orla Coffee, congratulations. You've won a €100 lifestyle sports voucher. Spend it wisely and have a very active couple of weeks ahead with whatever you spend it on. Look, I'm going to leave it there. I know we're pushing well past the time. I just, we've gone through as many questions as we can. So, Dan, Rob, thanks again so much for an informative presentation. We're getting lots of really positive feedback from everybody there. Such great attendance in the hundreds for physics, which is amazing. So thank you so much. Thank you to all the teachers joining us this evening. You're straight back in at the coal face with a brand new specification to teach, only a couple of days. So you're probably up the walls as it is. So we really appreciate you taking the time to be here with us. If you have any further questions, if I've not answered any questions that you've asked, I can hear them still coming through. Unfortunately, I couldn't get to everything. So please don't hesitate to get in touch with your Folan's rep and we'll help in whatever way that we can. So we'll leave it there. I hope you have a good first week back to school and thanks so much for joining us. Take care, everybody.